Welcome, ladies and gentlemen, to your second part, Part B of Section 7.6, which is where we're solving exponential and logarithmic equations. In this Part B video, we are going to be applying what we've known. So we put Part B there, application. We have three examples, and these are really, really powerful examples because it brings into the class compound continuously interest formula and the compound just the general compound interest formula. So some of you may have been exposed to it, some of you may not, and I just think it's really important that it's my job to make sure that as you leave school that you have some exposure to how interest is compounded, whether it's an investment, banking, or bills. So let's kind of start with example 6, which is taking us back to really the earlier part of the chapter where you're buying a new mountain bike for $400. The value, of course, decreases in value at 15% each year. When will the bike be worth $200? And what I mean by taking you back to the earlier, remember when we said we have y equals ab to the x, where a is the initial amount, b is your growth or decay factor, not your percent decrease, but your factor. X is your time typically, and then Y is your end value. So in this case, what's really nice is we know that 400 is going in for A. We know that the value is 200, so I'm going to put 200 over here equals 400. You know, I don't want to be too redundant of what I did in earlier chapters, but or sections. But what I do want to say is the B, which is that growth or decay factor. Again, just a reminder that you do not put 0.1. First of all, you don't use 15% because we always use in calculations it in decimal form. But this is how much is taken away. So what we need to make sure is that we understand that the B, which is the growth or decay factor, is what's remaining when we're talking about decay. So that's talking about 0.85. That's what remains, or 85% if you want to think of it that way. So don't use the 0.15 in here, you're using the 0.85. So again, the growth or decay factor is what remains, not what's been taken away. So 15% is taken away, 85% remains every year, so that's why we're using 0.85. And then I'm going to change this over to t because we are looking for when, time, how many years will it be when the bike is worth $200. So as in the past, I said you have to isolate this completely. Now I do want to say that we've done a lot of these, and I showed you how to solve this by graphing. And the reason for that is because you did not have the tools to do what I'm going to show you now, which you'll see is much quicker than graphing. So 200 over 400 is 0.5 or 1/2. I'm just going to go 0.5 equals 0.85 t. And again, this is where you would have put this into y1, this into your y2, and go from there. But I need to make sure I show you everything. That is clearly not the only way to solve these. Now we know how to get a variable out of the exponential spot. We know how to solve this. And you can do one of two things. One is you can just do the change of base really, or excuse me, you can take the log of both sides really quick. And that's what I'm going to show you first. And just for I don't know why I did this, but in my notes I actually use natural log. So I'm going to take the natural log of both sides of this equation, just like we did earlier, and note that we can take that t down. And I don't know if you want, I'll do it afterwards. I was going to do it all in one great big swooping motion. So now, once we take natural log of both sides of this equation, we can bring this t down and solve it from there. So we can say that the nat t is equal to the natural log of 0.5 divided by the natural log of 0.85. And when you solve that, you'll end up with that t is equal to 4.27 years. Now, what I just showed you is how I do it. This is absolutely how I do it because it's the most straightforward. So to get a variable out of the exponential spot, the most powerful way of doing that is by taking the log or natural log of both sides, because then from there you can just bring that variable down, exponent down, using the logarithmic product property, or power property, excuse me, the third property that I taught you, and then you can solve it from there. Now what I said is that there was more than one way of doing it. At this point right here, if you really want, you could switch it over to this exponential equation over to a logarithm equation, which would be log base 0.85 0.5 equals t, and then you can do the change of base on that. Log 0.5 over log 0.85. And you know what? You notice up there, it'll give you the same answer. So it's, again, however you want to do it. But with that said, the power is that of logarithms is that you can solve variables that are up in the exponent spot. That is the only way you can solve equations accurately when they're up in the exponential spot. So exponential equations, you use logs to solve them. Okay, so again, just as a reminder, nope, I don't want to erase that. You could either show this work right here. Actually, you would have to show the setup. You'd have to show down here, and then switch it over to if you're going to do the change of base. Or, again, you can go and show, and I'm just saying this because you can use your calculator, I realize, some of you. Otherwise, you have to show this, all the purple, this with this. So you have to show one of the two strategies here, whichever you choose. Okay, so with that said, coming up down here, it says example 7. At what interest rate, compounded continuously, would you need to invest $200 in order for it to triple in 6 years? So what we want to know is, I want to know in 6 years, I want my money to go from $200 to $600. So I need to know the interest rate. I don't know if you've ever seen this, but I want to make sure you get exposure to this. This is the compounded continuously, which means that it's compounding, the interest is compounding so fast, so much faster than even a second, a quarter second, a third, or an eighth of a second, and so on. That this is the compounded continuously formula. Notice it's using the number e, but a is the amount at the end equals p principal e raised to the rt. Notice it looks very similar to our y equals ab to the x. Now, I want to put the values we know. We know that the p, the principal, is equal to 200, and yes, it's spelled the same way as the principal of a school, PAL. So just kind of making sure that you don't spell it like I stand alone on principle. So principal is how you spell this principal anyway. The rate, well, actually, the end result, the A, we know is going to be 600. That's how much we want it to be worth. The rate is what we're trying to find, and the T is 6 years. So I just want to let you know you can use this formula for anything. You could find, like, if you know your interest rate and how much time and the principal, you can find out how much your investment is worth or how much your credit card is going to be worth. Because I will say, investments are not continuously. If you can find one, tell me, because I'd like to invest my money into that. What tends to happen is continuously is the credit cards. So that's where you hear that they compound so fast. Some of them, like mine, compounds daily. Continuously tend to be more of the lower end cards when you don't have much of a credit rating, which just so happens to be usually university students. And that's kind of how they get themselves into financial trouble. So just kind of be aware of that. This is a conversation I love to have with anyone who wants to know more about finance, because that is kind of one of my specialties. Anyway, so I'm going to put these values right into our equation or our formula. So we have 600 equals the principal, which is 2, e raised to the rate, which we don't know, times 6. Now, I do want to say again that it's pretty straightforward to use this formula. Sometimes people remember it by, notice how this spells pert, like everyone's so nice and pert. I don't know. But for whatever reason, people remember that. There's also other mnemonics, but it does spell the word pert, if that helps you remember it. I do want to say that I give you these formulas on any kind of assessment, because at this point, you need to know how to use them, but you don't need to have them per se memorized. I'm dividing out by 200, which gives me 3 equals e to the 6r, and like I just said, you cannot solve exponentials where the variable is in the exponential spot without logs. Now notice this is a base e, so I'm going to use natural log on both sides. And then I'm going to bring my exponent down, which is the power of that third property that we talked about. And we end up with 6r, actually I won't jump steps. Natural log 3 equals 6r natural log of e. Now if you take natural log of e in your calculator, you'll find out very quickly, because it's really e to what power gives you e? Well, e to the first gives you e, right? So this equals 1. So you have 6r equals natural log of 3, and then you can divide it by 6, and you end with r equals this. You throw in the calculator, you'll end up with 0.1831, which of course we would switch over to 18.31%. Now, there's nowhere in this world that you're going to find an interest rate compounded continuously that you can invest in with an interest rate of 18.31. To give you an idea, savings accounts, money markets are at like 2-3% compounded quarterly. Savings accounts are less than that, and they're compounded either quarterly or even every half year or semi-annually. If you invest in like the Roth or like the stock market, that's different. That's going to be compounded sometimes daily, sometimes, it's all sorts of different things. And if the market's going really, really well, you can get up to maybe sometimes a really high percent, but on average, it again, depending on what you're investing in and how risky it's going to be, you tend to try to go for somewhere between the 6 to 10% range. So 18.31% is not going to be anything you find in the market to increase your money. But I will say this, that credit cards, this is where you're losing money, of course. Credit cards, to find an 18.31% rate might actually pose difficult for you all. You're going to be more like about the 24% to 28% interest rate compounded continuously or daily. Just saying. So looking at this, if you do spend $200 in 6 years, you'll actually end up paying triple what you initially charged, which is exactly what happens. And actually, it would be tripling much faster than that for you guys, because you won't be finding an interest rate at 18.31%. But anyway, again, if you have questions about that, please let me know. Love talking about it. Well, I know although I do make it sound depressing though, but I do want you to be very, very aware of credit, especially those credit cards, which I of course use them, and they're great for accounting matters, but you do need to make sure that you can pay those suckers off on a monthly basis. So those credit card companies, they charge 3% of the companies that are using them, and then they're charging you all for not paying it off, and oof, they make a good dollar amount on those. Anyway, okay, example 8. It says, how many years will it take to triple your money if you invest at a 6% interest rate? This is a little bit more typical of an interest rate in, let's say, a 401k, if you're lucky, assuming that you're not talking about 2008, 2009 of this year, or in the past, because everyone lost money. Anyway, so looking at this, it's compounded quarterly. And again, I hope at some point you have been exposed to this interest rate formula. You'll never, in my class, would have to memorize it, just because it's important to know how to use it, but a lot of times you can just look it up really quick. Of course, if that changes depending on what class we're talking about, because pre-calc they're expected to know it, just kind of keep in mind, you could always ask me if you worry that I'm going to give it the formula to you or not, which in advanced alg I do give it to you. Okay, so how many years will it take to triple your money? So we know, actually notice they're not giving you any money value. So you can say, I'm investing $100, so how long will it take to get to $300? But really what makes it easiest, if it does this kind of thing where it says what's for tripling, I would just say, invest $1 and my output or my end result I want to be $3. But again, you can do, just because of the triple component, you can put any money in. If you want to put $1,000 in and want to know when you'll get $3,000, it's just, The bigger the numbers, the more you're going to have to do. But I'm just letting you know that this is the trick. You just can put $1 in and wonder how long it takes to get $3. Excuse me. The rate in this case is 6% or 0.06. The n notice is the number of times compounded, and notice it says quarterly, so we're going to put 4 in for n. That's quarterly. And then the t, the number of years, is what we're trying to figure out. And notice this is definitely a little bit more complicated formula, but this is a very, very typical kind of investment thing. Quarterly, your savings account, if you have one, is most likely quarterly. Some of them are monthly. But if it's monthly, you would say 12 here for n. If it's daily, you'd say 365 for n. So that n value is just how many times it's compounded in a course of 1 year. Okay, so I'm going to put the values in. So the a value is 3 equals, the p is 1, 1 plus the rate is 0.06% or 6%, which is 0.06, compounded quarterly, and then we have quarterly here times t. We don't know. That's kind of what we're trying to find here. Now the trick to this formula, folks, is to make sure you do your order of operations right. So I have 3 equals 1. This in here, this 1 plus 0.06 divided by 4. So in your calculator, go 0.06 divided by 4, hit enter, then add your 1. You'll end up with 1.015 4 to the t power. The 1, this is where I'm saying if you put a big number like 1,000 and 3,000, all you're going to end up at this moment is dividing that out so you can isolate your exponent. But because we used 1, we don't even need to worry about this, right? So we have 3 equals 1.015 raised to the 4t. And this is where you take the natural log or log of both sides. Of course, if you were graphing it, you'd put the 1 in y1, the 1 in y2, and find the intersection. But this is where I'm saying it's faster to use logs. And I'm going to actually do this in one great big swooping motion here. I'm going to notice I'm moving this down right away, right here, because we've been doing it a while and I'm running out of space. And so at this point, you're going to divide both sides by log of 1.015, start solving for it, right? Log 1.015, and you end up with, and I'm coming over this way because I'm running out of space, 73.7888 equals 4t, and then I'm going to divide out by 4 to solve for t, and it's going to take approximately 18.45 years to get a amount to triple at a rate of 6%. So, the example 7, you're like, well, hold it, that one, it was only 6 years. Yeah, but 6 years at 18.31%, which is a huge percent rate for any kind of investment. But it's going to take you about 18.5 years to triple your money in a Roth, let's say, if you have a Roth or a 401k or a school. If you can ask your folks if they have some sort of Edvest or some sort of investments for your higher education. But what I tell my own children is if they start investing young now, at an average of, let's say, a little bit over 6% in any kind of like stock market-ish kind of thing. So if they can average like somewhere between 6 and 8%, you're talking about tripling your money in what seems like a long time, but when you're a kid and all of a sudden you're 20, 30, 40 years old, that's a lot of money very quickly. So especially the 401k, you kind of hear invest in your retirement early. That's because when it's compounding, that interest is then being put back on your principal, and it's going to be compounding your original principal plus all the interest you earned. So if you can start early, the original principal that you invested, it's going to be much larger, and you're just going to have a much larger base to get interest on. So again, any questions on that? I love talking about it. It's one of those things I kind of dig. So if you have any questions about this, let me know. But those were the 3 examples that I thought were going to be most powerful for you. Again, notice all of them at the end have an exponent with a variable. So that's why we take the log or natural log of both sides to solve that, so we can bring that exponent down. Okay, well, if any questions, we'll answer them in class. Take care.